everyone, welcome to CH4S. Today we will be solving few questions which have appeared in the NET examination.
Seeing the first question, where this reactant undergoes oxidation in the presence of selenium dioxide. So this is the structure of selenium dioxide. Oxygen here will take the bond from selenium and will get a negative charge on oxygen. Selenium will be getting a positive charge. In this reactant, the double bond present between these two carbon atoms is shifted onto this carbon, leaving this carbon negatively charged, and this carbon will be getting a positive charge. Now, as this carbon is positively charged, the bond present between this carbon and hydrogen is shifted here, forming a double bond between these two carbons. And this hydrogen will be eliminated as H plus from this compound. Now, this negatively charged carbon will form a bond with the positively charged selenium and will give us a structure like this. A bond is formed between carbon and selenium. Now this released H plus, it will form bond with this negatively charged oxygen and will give us an alcoholic group here. Now in this structure, the doubly bonded oxygen will take one of the bond from selenium and will get a negative charge. Selenium will get a positive charge. As the selenium is positively charged, it will take the bond from carbon and this carbon will be getting a positive charge. Now after this reaction we will be getting two different compounds. Oxygen is negatively charged, the carbon here is positively charged. As this carbon is positively charged, the double bond present between these two carbons is shifted here and the carbon here will be getting a positive charge now. Now this positively charged carbon will form a bond with the negatively charged oxygen and a bond is formed between carbon and oxygen. Now what happens here is, as oxygen is more electronegative, it will take the bond from selenium, leaving the selenium positively charged. And the bond present between this oxygen and hydrogen is shifted here. Hydrogen will be removed as H plus and this H plus will come and form bond with the negatively charged oxygen, giving us an alcoholic group here at this carbon atom. Now the selenium and oxygen will be removed as selenium oxide. So this is our final product when this reactant undergoes oxidation in the presence of selenium dioxide. Now, we'll see the next question. So here, citronellal will react with dimethyl malonate in the presence of NaOMe and later on it will be heated. So it will be giving us one product. We have to find what is this product. So, this is citronellal and this is dimethyl malonate. In dimethyl malonate, we will be having two carbonyl groups. So, one of the carbonyl group, oxygen will take the bond from carbon, leaving this carbon positively charged. See, this carbon will be getting a positive charge and this carbon will get a negative charge. Now, as this carbon is positively charged, the bond present between this carbon and hydrogen is shifted here and a double bond is formed between them. Now, this hydrogen is released as H plus. Now in citronellal, this is the aldehyde group. So oxygen here will take the bond from carbon, leaving this carbon positively charged. Oxygen will be getting a negative charge. Now this released H plus from dimethyl malonate will form a bond from this. It will form bond with this oxygen, and OH alcoholic group is formed. See, this alcohol group is formed. Now this carbon is positively charged. So we have to make this attack with a nucleophile. So for that what happens here is, the negative charge on oxygen is shifted between this carbon and oxygen, forming a double bond, and this extra bond is taken by this carbon, leaving this carbon negatively charged. Now this negatively charged carbon will be acting as a nucleophile and that will attack the electrophilic carbonyl compound present in citronellal. So a CC bond formation is seen here. This is the CC bond formation. Right. Now whatever the alcoholic group is present on this, see, this is the alcoholic group we have written here. It will be eliminated as OH minus and the carbon will be getting a positive charge. See, this carbon is getting a positive charge. Now we have a double bond in citronellal, right? In citronellal we will be having a double bond. So this double bond is shifted onto the third carbon, 1, 2, 3. So this double bond is shifted onto the third carbon, leaving the second carbon positively charged and this third carbon will be getting a negative charge. Why we are shifting this double bond onto the third carbon? Because when we shift it onto the third carbon, this here will be forming a tertiary carbocation, which is more stable than secondary carbocation. Now, when a tertiary carbocation is formed, see this is a tertiary carbocation, and here we will be getting a negative charge on the carbon. So, the CH3 present here, the bond between this carbon and hydrogen is shifted here. See this carbon and hydrogen, any one of the bond will be shifted here, forming a double bond between these two carbon atoms, and this hydrogen is released as H plus. Right, see here double bond is formed between these two carbons, H plus is removed, and this nucleophile, this negatively charged carbon will attack the positively charged carbon, forming a ring, 6-membered ring. So this is the final product we get when citronellal reacts with dimethylmalonate and further when it is heated. So this whole reaction is called as Knoevenagel condensation reaction. So what is this Knoevenagel condensation reaction? The attack of nucleophile on this electrophile followed by dehydration is called as Knoevenagel condensation reaction. So now we'll see the next question. Here the reactant is undergoing oxidation with PCC in the presence of CH2Cl2, that is dichloromethane. So what is this PCC? Pyridinium chlorochromate. This is the structure of pyridinium chlorochromate. Now we'll see the mechanism for this reaction. We have taken the reactant reacting with PCC, that is pyridinium chlorochromate. In this pyridinium chlorochromate, oxygen, the doubly bonded oxygen will take the bond from chromium, leaving this chromium positively charged. Oxygen here will be getting a negative charge. Now, the oxygen, the alcoholic group which is present in the reactant, this oxygen will share its lone pair of electrons with the positively charged chromium, forming a bond between oxygen and chromium like this. So we will be getting a structure after that reaction. As oxygen here is forming 3 bonds, it is getting a positive charge on it. So it will take the bond from hydrogen, and this hydrogen will be removed as H plus. Now this positively charged hydrogen will form bond with the negatively charged oxygen, and an alcoholic group will be getting here, an hydroxy group. Now what happens here in this compound? We will be eliminating chlorine as Cl minus. When Cl minus is removed, chromium here will be getting a positive charge. Right. So when this chromium gets a positive charge, this oxygen will take the bond from carbon, and a double bond is formed between chromium and oxygen, leaving this carbon positively charged. See, this carbon here will get a positive charge. Chlorine is removed, and here double bond is formed between chromium and oxygen. Now what happens? This negatively charged oxygen will attack the positively charged carbon here and will form a bond between carbon and oxygen. So this is the structure we get after this reaction. Here what happens? As oxygen is more electronegative, this bond is shifted between chromium and oxygen. Hydrogen is removed as H plus. Now as chromium is carrying how many bonds? 7 bonds. One of the bond is shifted onto this oxygen. So that negatively charged oxygen will share its extra electrons here, forming a double bond between carbon and oxygen. Now here carbon is carrying more bonds, that is 5 bonds. So one hydrogen is removed as hydride ion, that is H minus. So H plus and H minus will be removed as H2. And this CrO3 is also eliminated in this reaction, giving us an aldehyde. So what happens first? The oxygen here in the aldehyde position will take the bond from carbon, leaving this carbon positively charged. Oxygen will get a negative charge. Now another oxygen, that is the hydroxy group present here. The oxygen will take the bond from hydrogen. Hydrogen will be removed as H plus. Oxygen will get a negative charge. This oxygen also gets a negative charge. Carbon here will get a positive charge. negatively charged oxygen will attack the positively charged carbon and a 5-membered heterocyclic ring is formed. Here this carbon will be carrying a negatively charged oxygen as well as a hydrogen. Now what happens, this negatively charged oxygen will share its extra electrons here and a double bond is formed between carbon and oxygen like this. And this hydrogen will be removed as H minus. So we will be getting our final product, that is an ester. Now we will see the next question. So what is the product formed and the process involved in the following reaction? This reactant is heated to give us a product. We have to find what is this product and the process involved in this reaction. So here in the reactant we can see conjugated double bonds, right? And now the sigma bond present here between these two carbons is shifted here. See here, it is shifted here. This double bond is shifted here. This double bond is shifted here, and a new sigma bond is formed between these two carbons. Now this double bond is shifted here. This double bond is shifted here. So after the shifting of these double bonds, we will be getting a structure like this. This sigma bond is breaking and here a new sigma bond is formed. Right. So the breaking of sigma bond and the formation of new sigma bond is called as sigmatropic rearrangement. Now we have to see what type of sigmatropic rearrangement is seen in this given product. So here what happens is, these two ends are of a sigma bond and even these two ends are of a sigma bond. So the number of atoms present between these two ends and the number of atoms present between these two ends gives us the type of sigmatropic rearrangement. So here we have 1, 2, 3, 4, 5 atoms present between these two ends. And here we have 1, 2, 3, 4, 5 atoms present between these two ends. So it is a 5, 5 sigmatropic rearrangement. 5, 5 sigmatropic rearrangement. Now, here in this compound we can see that oxygen is negatively charged. So we will be adding one proton to this compound and we will be getting a hydroxy group here. And now this hydroxy group is converted into a ketone group. How? The bond present between oxygen and hydrogen is shifted between carbon and oxygen and a double bond is formed. This hydrogen is removed as H+. Now as this carbon is carrying 5 bonds, one of its bond will be taken by the adjacent carbon and that carbon will be getting a negative charge. Now this released H+ will go and form bond with the negatively charged carbon and we will be getting our final product. So this is our final product and this whole reaction is called as 5, 5 sigmatropic rearrangement reaction. So now we will see the next question. The major product A and B in the following reaction is, this is a ketone reacting with an ether containing N-amino pyrrolidine and then it reacts with lithium diisopropylamide at minus 78 degrees centigrade and then it reacts with methyl iodide to give us product A. And this product A will undergo ozonolysis to give product B. We have to find both product A as well as product B. Now we will be taking ketone here which is reacting with ether containing N-amino pyrrolidine. So here we will eliminate water molecule from these two compounds and a double bond is formed between this carbon and nitrogen. This carbon and nitrogen, here a double bond is formed. Now this compound, it will react with lithium diisopropylamide which is a very strong base. So it will remove protons from this compound. So here the bond between this carbon and hydrogen is taken by this carbon leaving hydrogen as H+. So we have removed one proton and this carbon will be getting a negative charge. Now this negative charge is shifted here. This double bond is shifted onto the nitrogen leaving nitrogen negatively charged. Now again this negative charge of nitrogen is shifted here and this double bond is shifted onto the carbon leaving this carbon negatively charged. Now this compound is reacting with methyl iodide. In methyl iodide, iodine leaves as I- and this methyl group will be getting a positive charge. Now this positively charged methyl group will form a bond with the negatively charged carbon and will give us the product A. So this is the product A. Now this product A will undergo ozonolysis, that is it will react with ozone, which is O3. This is the structure of ozone where one oxygen is positively charged and one more oxygen is negatively charged. In this product A, nitrogen will take the bond from carbon, leaving this carbon positively charged, nitrogen will get a negative charge. Now this negatively charged oxygen will form bond with the positively charged carbon. This positively charged oxygen will form bond with the negatively charged nitrogen, giving us a 4-membered heterocyclic ring. Now this oxygen here will be carrying 2+ charge. This oxygen will take the bond from oxygen and will get a negative charge on this. This oxygen will now carry positive charge. Now to this negatively charged oxygen, we will be adding one proton and we will get a hydroxy group here. This hydroxy group is eliminated in the presence of H+ as water molecule. And now what happens here? The bond between carbon and nitrogen is shifted here. The bond between these two oxygens is shifted here, giving us ketone, that is product B. And this product is eliminated. This is a byproduct. This is our final product B.
For more such sessions, please do like, share and subscribe our channel. Thank you.